In the next section you will learn how to assess the performance of a cooling tower. The performance of cooling towers is evaluated to assess present levels of approach and range against their design values, identify areas of energy wastage and to suggest improvements. During the performance evaluation, portable monitoring instruments are used to measure the following parameters: wet bulb temperature of air, dry bulb temperature of air, cooling tower inlet water temperature, cooling tower outlet water temperature, exhaust air temperature, electrical readings of pump and fan motors, water flow rate, air flow rate. These measured parameters and then used to determine the cooling tower performance in several ways. These are range, approach, effectiveness, cooling capacity, evaporation loss, cycles of concentration, blow-down losses, liquid/gas ratio. We will now go through each of these parameters on the next slides. The range is the difference between the cooling tower water inlet and outlet temperature. The formula for cooling tower range in degrees Celsius is cooling water inlet temperature minus cooling water outlet temperature. A high cooling tower range means that the cooling tower has been able to reduce the water temperature effectively, and is thus performing well. Approach is the difference between the cooling tower outlet cold water temperature and ambient wet bulb temperature. The formula for approach is cooling tower approach in degrees Celsius is cold water outlet temperature minus the wet bulb temperature. The lower the approach, the better the cooling tower performance. Although both range and approach should be monitored, the approach is a better indicator of cooling tower performance. Cooling tower effectiveness is the ratio between the range and the ideal range, in percentage, for example, difference between cooling water inlet temperature and ambient wet bulb temperature. Effectiveness equals range divided by range plus approach. The formula for cooling tower effectiveness is cooling tower effectiveness percent equals 100 multiplied by the difference between cooling water inlet temperature minus cooling water outlet temperature, divided by cooling water inlet temperature minus wet bulb temperature. The higher this ratio, the higher the cooling tower effectiveness. Cooling capacity is the heat rejected in kilocalorie per hour or tons of refrigeration, given as product of mass flow rate of water, specific heat and temperature difference. High cooling capacity means good performance. Evaporation loss is the water quantity evaporated for cooling duty. Theoretically, the evaporation quantity works out to 1.8 meter cube for every 1 million kilocalorie heat rejected. The following formula can be used: Perry. Evaporation loss, meter cube per hour, equals 0.00085 x 1.8 x circulation rate, meter cube per hour, x, T1 T2. T1, T2 equals temperature difference between inlet and outlet water. Equals of concentration, C.O.C, is the ratio of dissolved solids in circulating water to the dissolved solids in makeup water. Blow-down losses depend upon cycles of concentration and the evaporation losses. Blow-down losses is given by the following relation: blow-down equals evaporation loss slash cycles of concentration 1. The L/G ratio of a cooling tower is the ratio between the water and the air mass flow rates. Cooling towers have certain design values, but seasonal variations require adjustment and tuning of water and air flow rates to get the best cooling tower effectiveness. Adjustments can be made by water box loading changes or blade angle adjustments. Thermodynamic rules also dictate that the heat removed from the water must be equal to the heat absorbed by the surrounding air. Therefore, the following formulae can be used. Mention that these are the same formula, just written differently. L, T1 T2, equals G, H2 H1. L by G equals H2 H1, by T1 T2. Where L by G equals liquid to gas mass flow ratio, kg by kg. T1 equals hot water temperature, degrees Celsius. T2 equals cold water temperature, degrees Celsius. H2 equals enthalpy of air-water-vapor mixture at exhaust wet bulb temperature, same units as above. H1 equals enthalpy of air-water-vapor mixture at exhaust wet bulb temperature, degrees Celsius. H2 equals enthalpy of air-water-vapor mixture at exhaust wet bulb temperature, same units as above. H1 equals enthalpy of air-water-vapor mixture at inlet wet bulb temperature, same units as above.